In this video, we're discussing learning outcome number 2 of lesson 9.2, which is about testing a claim about two proportions using the p-value method. So we're just going to work through an example. This example is very similar to the problems that you'll see in your homework. And we will tend to use technology to compute the corresponding or the necessary probabilities. But we could also use table A2 to compute those probabilities because our test statistic happens to be a z-score from that standard normal distribution. So let's look at our problem statement. It says, in a study of Burger King drive-through orders, it was found that 264 orders were accurate and 54 were not accurate. For McDonald's, 329 orders were found to be accurate, while 33 were found to be inaccurate. We're asked to use a 0.05 significance level to test the claim that Burger King and McDonald's have the same accuracy rates. We're asked to use the p-value method with a normal distribution as an approximation to the binomial distribution. As part of the solution to this problem, we're going to be asked to identify the null and alternative hypotheses. We're going to be asked to compute the test statistic and find the corresponding p-value. And after we find that p-value, we want to compare it to alpha and use that to come up with a conclusion about the null hypothesis, as well as a final conclusion that addresses the original claim. So the first thing we want to do in any hypothesis test is check to make sure that those requirements for the hypothesis test are met. So in this case, we'll just assume that both samples are simple random samples. If we had access to the original data and probably a write-up associated with that data, we would see that these two samples are simple random samples. The second requirement is that the samples are independent from each other. There's no reason certain orders from the sample would be matched or paired with specific orders in the other sample. So the two samples seem to be independent from each other. And then lastly, there are at least 5 successes and 5 failures in each sample, so it is appropriate to use a normal distribution as an approximation to the binomial distribution here. Now, if we look at that last slide, let's just look at it. If we say that an accurate order is a success, for the Burger King drive-through orders, we had 264 accurate orders, so that's 264 successes, and 54 that were not accurate, so it's 54 failures. Clearly, both of those numbers are greater than 5. And the same is true for the McDonald's orders. We've got 329 accurate orders, so that's 329 successes, and 33 inaccurate orders. So those are 33 failures. 329 and 33 are both greater than or equal to 5. So we can say that it is appropriate to use a normal distribution as an approximation to the binomial distribution here. If the first 2 requirements are satisfied, but the last one isn't, then we could use a binomial distribution. But that's relatively complicated and beyond the scope of this class. So in this class, we're just going to use that normal distribution as an approximation to the binomial distribution. Okay, so the requirements are met. Next thing we want to do is what we always do. We want to identify the null and alternative hypotheses by looking at the claim, stating it in symbolic form, and then stating what would have to be true if the claim is not true, and then using that to infer the null and alternative hypotheses. So the claim in the problem statement was this: Burger King and McDonald's have the same accuracy rates. So that's saying that the probability of getting an accurate order at McDonald's is the same as the probability of getting an accurate order at Burger King. Or alternatively, the proportion of accurate orders at McDonald's is the same as the proportion of accurate orders at Burger King. So the claim is that P1 and P2 are equal to each other. I'm using P1 to represent the proportion of accurate orders at Burger King, and I'm using P2 to represent the proportion of accurate orders at McDonald's. Now, if that's not true, P1 and P2 are not equal to each other. Now, if I'm trying to identify the null and alternative hypotheses from here, I just look at these 2 statements and I look for the one that does not contain the condition of equality. That's the second one. That's our alternative hypothesis. And then the null is exactly like the alternative hypothesis, but you just change that not equal to sign to an equal to sign, or an equal sign. Okay, so this is a part of the problem statement that's necessary for the next part of the solution. After we've stated that null and alternative hypothesis, it's appropriate to identify or compute sample proportions as necessary and identify sample sizes. You have to be really careful on this problem. A lot of students will assume that with the Burger King drive-through orders, the smaller number between these two numbers is your X and the larger number is your N. So they might say that X1 is 54 and N1 is 264, but that's not exactly right. X1 is the number of accurate orders at Burger King, and the sample size from Burger King is the number of orders from Burger King. So that means we have to take the inaccurate orders and the accurate orders and add them together to get the true sample size. Don't just randomly divide 54 by 264. Think about what these numbers mean. You've got to find the sample size, find the number of successes, however you choose to define success. I'm choosing to define it as an accurate order, and then compute that proportion. In this case, the proportion is 44 over 53, which is approximately 0.830. For the second sample, we got to do the same thing. We want the number of accurate orders from McDonald's in the numerator. And they told us that there were 329 accurate orders at McDonald's. Out of the total number of orders from McDonald's, well, there were 329 of them, and then there were 33 more that were 329 that were accurate and 33 more that were inaccurate. So if we add those together, we have 362 in our sample. And if you divide those, you get approximately 0.909. So we've got our P1 hat and P2 hat, and N1 and N2 are 264 plus 54, so that looks like 318, and 329 plus 33, which is 362. Okay, now this is not a necessary step, but I like to include this in the procedure because it demonstrates that you are thinking about the sampling distribution of P1 hat minus P2 hat and how that corresponds to the test statistic Z that we're going to compute in a little bit. So I would like for you to graph a sampling distribution of P1 minus P2 or P1 hat minus P2 hat, assuming that the null hypothesis is true. So it's assuming that P1 and P2 are equal to each other. And then we want to label the value of the sample statistic that we have, that difference between P1 hat and P2 hat. We want to label that on the graph. And then we're going to use the assumption that the null hypothesis is true to compute the appropriate standard deviation in terms of the pooled sample proportion. Okay, so if the null hypothesis is true, P1 equals P2, that means that P1 minus P2 would have to be 0. Now P1 hat minus P2 hat is just that proportion minus that proportion. And if we take a decimal approximation, we see that P1 hat minus P2 hat is approximately negative 0.078 or 7865. So this is our sampling distribution or a distribution of P1 hat minus P2 hat. And we know that the mean of this distribution of P1 hat minus P2 hat is equal to the true population proportion P1 minus the true population proportion P2. That's a very nice property. But we're assuming when we draw this distribution that the null hypothesis is true. So we're assuming that P1 and P2 are equal to each other. So that means we're assuming that the mean of the sampling distribution of P1 hat minus P2 hat is equal to 0. And then we're saying, okay, if the mean is equal to 0, how likely is it that we get a P1 hat minus a P2 hat equal to approximately negative 0.07865? Is that value of P1 hat minus P2 hat significantly low, given that the null hypothesis is true? If it is significantly low, then we'll throw out the null hypothesis and say it's probably not true if we have this improbable thing happening. If something is supposed to be improbable, but it's happening, well, then maybe it's not that improbable after all. And whatever assumption led us to believe it was improbable is incorrect. So in this case, the assumption is that the null hypothesis is true. So again, we're trying to figure out whether P1 hat minus P2 hat is significantly high or significantly low, given that the null is true. In order to determine whether that's significantly low, we're going to compute the corresponding test statistic. And this requires computing the pooled sample proportion, P bar, as we discussed in the last video. So P bar is the proportion of success in a larger sample that we're thinking of as just the combination of the first sample and the second sample. And I hate that I just used the word combination in the statistics class in that way, but I hope you understand what we mean. We're just going to put the two samples together and we're going to make one large sample. The original first sample had 318 orders in it, and the original second sample had 362 orders in it. So total, we have 680 orders here. Now, we had 264 accurate orders from one of our restaurants and 329 accurate orders from the other restaurant. That means we had 593 accurate orders in general. So P bar is the proportion of accurate orders out of all of the orders that we were looking at, and we're disregarding which restaurants they come from. So we had 593 accurate orders out of 680, which is about a proportion of about 0.872. Now, if you're saying to yourself, what is that? Why do we do that? Remember, we talked about it in the last video. When we are assuming that the null hypothesis is true, we're assuming that P1 and P2 are equal to each other. But we don't actually have a value for P1 or P2. All we have are these point estimates of P1 hat and P2 hat. You might say, okay, well, we've got these two different point estimates. What's the best estimate that we have of the common value of P1 and P2 if they're truly equal to each other as stated in the null hypothesis? Well, the best estimate we have of P1 and P2 at the same time is this P bar, this pooled sample proportion. So this is the value of P that we use in that standard deviation formula for a test statistic Z. And again, it comes from the fact that we're assuming that the null is true, which means we're assuming that P1 and P2 are equal to each other. And then we're saying, if they are equal to each other, what are they equal to? We're saying it's approximately this. They're approximately equal to this P bar. We need Q bar for our formula as well. So you just take the complement of P bar, and then we substitute everything into our formula. Now you can type all of this into your calculator. You see they've got a lot of fractions there. I used the exact fractions rather than the decimal approximations because I didn't want to lose any. I didn't want to lose any of my accuracy. So you could just type all of this into your calculator, but I highly recommend doing something different. So I'm going to show you how to do this in Excel now. Okay, so I created this little Excel spreadsheet, and in the first column, I'm listing N1, so that's the size of my first sample, and X1, that's the number of accurate orders in that sample. And then P1 hat, I'm having Excel compute that this way. Actually, I'll type in those formulas again for you guys. Now P1 hat is the number of successes in that first sample divided by the sample size. And similarly, for P2 hat, we get the number of successes in that second sample divided by the total sample size. So now I've got P1 hat and P2 hat, and then down here, I have Excel computing P1 hat minus P2 hat, and it's giving me that. Okay, so I need P1 hat minus P2 hat for my formula for the test statistic. We also need that estimate of the standard deviation that's in the denominator for our test statistic Z. In order to find that, we need to compute P bar, which is that pooled sample proportion. This is making a larger sample out of the two samples that we have by combining their sample sizes and combining their successes. So we're saying rather than having 318 orders from one restaurant and 362 orders from another, let's just say how many orders do we have? We have N1 plus N2 orders. So that's this number of orders plus this number of orders, and hit enter. And then we're going to say how many accurate orders do we have, regardless of which restaurant they come from. Let's It's going to be 264 orders plus the 329 orders, and you've got that number of successes. So we've got 593 out of 680. This is the exact same thing that you saw in the slides a moment ago. And if we take the number of successes and divide by the large sample size, we get that. And Q bar is 1 minus that. It's the complement. Okay. Now, to compute our test statistic Z, we need the estimated standard deviation for the hypothesis test, which is equal to the square root of, open parentheses, and then we're going to have P bar times Q bar, close parentheses, divided by the first sample size, plus, open parentheses for the second fraction, P bar times Q bar, close parentheses, divided by the second sample size, close parentheses again. The square root of that number is our estimate of the standard deviation that we're using in our hypothesis test. Okay, and I think that's enough to get our test statistic. Now remember, our test statistic Z is P1 hat minus P2 hat, so it's this value over here, minus P1 minus P2, that quantity, P1 minus P2, which is equal to 0, because we're assuming that P1 and P2 are equal to each other in our null hypothesis. So you would typically subtract 0. I'm not going to subtract 0 because it doesn't change anything. So our numerator is just P1 hat minus P2 hat. And the denominator is this estimate of the standard deviation that includes that P bar. And again, we're using P bar and Q bar because we're assuming that P1 and P2 are equal to each other, and P bar is our best guess for what P1 and P2 would be if they were equal to each other. So we just do that, and we get a test statistic of Z equals negative 3.06. And check it out, that's the same value that we would get if we typed all of that into our calculator. So I prefer typing it into Excel and having Excel do the computation. But you're going to do the same thing. You can just do it by hand on the calculator on a tiny screen, or you can do it on your computer in Excel. And I think Excel is more aesthetically pleasing, I think. So we get that Z-score, that's negative 3.06, and I want you to remember what it means. That is the Z-score corresponding to this P1 hat minus P2 hat. We're saying, if we compute this test statistic Z equals negative 3.06, what we're saying is that P1 hat minus P2 hat is 3.06 approximately standard deviations below the mean, provided that the mean of P1 hat minus P2 hat is 0, provided that there's no actual difference between the two proportions. Then the P1 hat minus the P2 hat that we found is actually 3.06 standard deviations below the mean. And that's relatively rare, pretty rare. The probability that's associated with that is this area in that left tail, and it's tiny. So we're just taking this distribution of P1 hat minus P2 hat, and then we're using this formula for the test statistic Z to convert from a non-standard normal distribution to a standard normal distribution. And we're saying, okay, well then P1 hat minus P2 hat under these conditions is approximately 3.06 standard deviations below the mean. Okay, now with the p-value method, the next thing we need to do is compute the corresponding p-value. Now, the p-value is always related to the area in the nearest tail. If it's a one-tailed test, it's just the area in that tail. If it's a two-tailed test, you find the area in the nearest tail and then you double it. So first we need to determine whether the test is two-tailed, left-tailed, or right-tailed. And we do that by looking at the alternative hypothesis. Since the alternative hypothesis includes that not equal to sign, we don't care if P1 is greater than P2 or P2 is greater than P1. If they're not equal, that's good enough for us. So we don't care if we're off on the left or on the right. If we're off, if the value of P1 minus P2 is significantly different from 0, then we're going to say that's enough to reject the null hypothesis. And we don't care if we're significantly high or significantly low in this case with a two-tailed test. Okay, so that means our p-value is going to be the area in the nearest tail, but doubled. Since our test statistic was on the left, we're going to find the area to the left of that test statistic, that's the area in the nearest tail, and then we'll multiply it by 2. So this is 2 times the probability that z is less than negative 3.06 approximately. You have 2 ways that you can compute this. One way is with table A2. This is what you would do if you did not have access to technology. So I'll show you how to do this using table A2 again. Basically, you just want to find the z-score of negative 3.06 and find the corresponding area in the table. Okay, so I look in this first column for negative 3.06. So there's negative 3.0, there's negative 3.00, 3.01, 2, 3, 4, 5, 6. And that's what we get. So the area to the left of z equals negative 3.06 is approximately 0.0011. And then we're going to double that, and that's our p-value. Now the other option is to use Excel to find that area to the left of z equals negative 3.06. Now that's my preference here as well, but we can use table A2 during our exams. To find the area to the left of z equals negative 3.06, we'll use the norm.dist function. You type in the z-score, the corresponding mean and standard deviation of the distribution it comes from. It's a standard normal distribution, so the mean is 0 and the standard deviation is 1. And then we'll say true, we want the area to the left. And if we take that and multiply by 2, we get the same value that we got using table A2. Let me show you how to do this in Excel now. I'm just going to type in this function here. Okay, so you go to the p-value, which I've already labeled here. I'll say 2 times norm.dist, open parentheses, and then I want the test statistic, and I've actually calculated it right there. So I'll use that rather than my approximation. The mean of the standard normal distribution is 0. Enter the standard deviation of the standard normal distribution, which is 1, and we say true. We want the area to the left, and then we want them to double it. And so we get that. And if we round to 4 decimal places, we get 0.0022, which is the same value that we got using table A2. Okay, great. So now that we have our p-value, we just need to compare our p-value to alpha and use that to make a decision about the null hypothesis. Since our significance level is 0.05, p is less than or equal to alpha. That means we'll reject the null hypothesis. Or in other words, we're saying that p1 hat minus p2 hat from our sample was significantly low, given that the null hypothesis was true. So we're saying, if something that is supposed to rarely happen is actually happening, then maybe the assumption that led us to believe that it was supposed to be rarely happening is incorrect. So we're going to reject that initial assumption, which means we're rejecting the null hypothesis. And then after we reject the null hypothesis, we have to state the conclusion in terms of the original claim in non-technical terms that anyone can understand. We don't want somebody to have to take statistics class to understand what we're talking about. So we go back to the original claim, look at that alternative and null hypothesis, and we see that the claim is actually the same as the null hypothesis. The claim was that the two proportions, the accuracy rate for McDonald's and Burger King, were equal to each other. So we're assuming that that's true. Okay, and then we were assuming that that was true, and assuming that that was true led us to reject the null hypothesis. We ended up with a very tiny probability for something that was happening. Anyway, what I want you to see here is that the claim and the null hypothesis are the same, and we're rejecting the null hypothesis. So if we're rejecting the null hypothesis, what we're really doing is we're rejecting the claim. So this is how we'll state our final answer. There is sufficient evidence to warrant rejection of the claim that Burger King and McDonald's have the same accuracy rates. Okay, so that is the p-value method. I'll see you in the next video to talk about the critical value method. This is also known as the traditional method. It's very similar. We can use Excel as well, but we also can use table A2. We can use that extensively here. Table A2 and table A3 are very commonly used for the critical value method, and we'll do that in the next video.